In the previous session, we have discussed about early adopter fiber amplifier, that is EDFA. Now we're going to discuss about the noise figure. Before going to discuss the noise figure, firstly, we have to discuss about its gain. Consider an optical amplifier, an optical fiber with a length of L. And if you're applying an input signal at the input side of the optical fiber, and we get the output after the length L, so the gain of the optical fiber, turbine optical fiber with a length of L is the G equal to PS of L divided by PS of O. That is the ratio of signal power at the fiber output to the signal power injected at the input fiber. Amplified spontaneous emission, ASG noise generates during amplification process is added to the signal, leading to decrease in signal to noise ratio at the amplifier output. Signal to noise ratio is nothing but that. I think you know that signal to noise ratio is the ratio of signal power to the noise power. And the noise figure also, I think you know that what is actually the noise figure. The noise figure is a ratio of signal to noise ratio at the input to the signal to noise ratio of the output. That is noise figure equal to signal to noise ratio input divided by signal to noise ratio of output. Noise figure can also be expressed in terms of gain and spontaneous emission factor also. That is noise figure equal to 2 times spontaneous emission factor into G minus 1 by G. That is equal to 2 times spontaneous emission factor. That is in terms of spontaneous emission factor and a gain G. So where spontaneous emission factor is equal to N2 divided by N2 minus N1, where N1 and N2 are the ionic populations into energy levels. Then now we are going to discuss about the semiconductor optical amplifiers, that's SOAs. Semiconductor optical amplifiers are nothing but that semiconductor laser amplifiers. They are in small size. As in the case of laser, it provides amplification by stimulated emission. I think all of you know about stimulated emission and population inversion that is taking place in the working principle of the laser. In semiconductor optical amplifiers, the amplification action takes place without reflection. Semiconductor optical amplifiers is of a gallium arsenide phosphide laser diode, which is operating below threshold. By changing the composition of indium gallium arsenide phosphide material, the gain of the amplifier can be varied. Then, while we are going to discuss about the working of semiconductor optical amplifier, it is like a traveling wave amplifier where many reflections do not take place in optical cavity. In semiconductor optical amplifiers using properties of semiconductor material, required gain to obtain in one pass of a light ray in optical cavity. So there is a like a traveling wave amplifier. So construction is similar to the laser diode. That's only. But in laser diode, the reflectivities of n phases are around 0.3. But in semiconductor optical amplifier, that is around 10 raised to minus 4. That is actually the difference between the laser diode and the semiconductor optical amplifier. In semiconductor optical amplifier, many reflections are avoided. To obtain the required gain, external charge carriers are injected. As the length of semiconductor optical amplifier is increased, the gain will increase. Okay, that is, if the length of semiconductor optical amplifiers increases, the gain of that amplifier will increase. That is important thing. So, how it increase the gain and other things we will discuss in next slide. By changing the material composition of indium gallium arsenide phosphide, maximum gain of in semiconductor optical amplifier that is obtained around 1200 nanometer and 1700 nanometer wavelength. A figure that's showing semiconductor optical amplifier structure, that is there is an input entering to the semiconductor optical amplifier and passing through it, and we will get the output from the semiconductor optical amplifiers. Okay, the working principle we can discuss in next slide. The basic working principle of an semiconductor amplifier, that is the same as a semiconductor laser but without feedback. Semiconductor optical amplifiers, SOAs amplify incident light through stimulated emission. When the light traveling through the active region, it causes these electrons to lose energy in the form of photon and get back to the ground state. Those stimulated photons have the same wavelength as the optical signal, thus amplifying the optical signal. In this figure, we can see that input signal that is applying into a semiconductor optical amplifier. When that light traveling through this active region, it causes these electrons to lose energy in the form of photons and get back to the ground state. Those stimulated photons have the same wavelength as the optical signal, thus amplifying the optical signal, and we get the output signal as in this figure. SOAs are of two types: traveling wave amplifier types and Fabry-Perot semiconductor optical amplifier. In traveling wave amplifier, N phase reflectivity is reduced to 10 raised to minus 4, and in Fabry-Perot semiconductor optical amplifiers, you can see that phase reflectivities are large about 0.3. Traveling wave amplifier is superior to Fabry-Perot as it is less independent on temperature fluctuations, bias current fluctuations, etc. Traveling wave amplifier has better noise characteristics. So a performance characteristics. A semiconductor optical amplifier is performance characteristics. The wide spectral bandwidth that may be achieved using high quality anti-reflection phase coatings on traveling wave amplifiers are in the region of 50 to 70 nanometer. Such devices require significantly higher bias current for operation. Traveling wave amplifiers are subject to increased levels of noise. Another important things in semiconductor optical amplifiers is crosstalk. I think all of you familiar with the term crosstalk. Consider an semiconductor amplifier, optical amplifier, that which is input the sum of two optical signals at different wavelength. Assume that both wavelengths are within the bandwidth of semiconductor optical amplifiers. The presence of one signal will deplete the minority carriers concentration by the stimulated emission process, so that the population inversion seen by the other signal is reduced. Thus, the other signal will not be amplified to the same extent, and if the minority carriers concentrations are not very large, may even be absorbed. Thus, for WDM networks, the gain is seen by the signal in one channel, whereas with the presence of absence of the signals in the other channel. That is actually this phenomenon is called the crosstalk. Okay, and it has a determinantal effect on the system performance. There are several ways of reducing the crosstalk introduced in semiconductor optical amplifiers. That is, in previously we have discussed about the crosstalks introduced in semiconductor optical amplifiers. One way is to operate the amplifier is the same is the small signal region. One way is to operate this amplifier in the small signal region where the gain is relatively independent of the input power of the signal. That is a method to overcome or eliminate the crosstalk. That is a method is that to operate the amplifier in the small signal region, because this small signal region is region that is the gain of the amplifier in this region is independent of power of the signal. That's why we can eliminate the effect of crosstalk. Another is to clamp the gain of the amplifier using a variety of techniques, so that even at the high signal power, its gain remains relatively constant, independent of the input signal. The crosstalk effect is not without its use. It can be used to make the wavelengths converter. These are the advantages of semiconductor optical amplifiers. To operate at 1300 nanometer and 1500 nanometer simultaneously. That is one of the advantages of the semiconductor optical amplifiers. Compact and can be easily integrable with other device. And another important thing is gain is independent of wavelength and having large band. And some disadvantages of semiconductor optical amplifiers are the polarization is in the semiconductor optical amplifiers are polarization dependence, has the polarization dependence, and it has high crosstalk and high coupling loss and immature technology, high noise figure, loss of linearity due to their bias current, and hence gain is rapidly reduced. These are the disadvantages of semiconductor optical amplifiers. And there are some applications of the semiconductor optical amplifiers that are used as a power booster, and they are used in inline amplifiers and pre-amplifiers. That is mentioned earlier in the starting of this module. We discussed that what is inline amplifier and pre-amplifier. These semiconductor optical amplifiers can use as a pre-amplifier or inline amplifiers, and also it can be used to wavelength conversion.